In this video, let's talk about how to integrate this rational function. And my goodness, it looks so innocuous, doesn't it? It looks so innocent. But to actually integrate this property, a lot of work will need to be done. Now, the first thing that I am noticing about this rational expression is that I would not be able to apply partial fraction decomposition on it right away, because the degree of the numerator is larger than the degree of the denominator, and I need the reverse to be the case. I need the numerator to have a smaller degree than the denominator in order to use partial fraction decomposition. So the first thing that I would have to do, step 1, is apply polynomial long division, because polynomial long division is a technique to reduce the degree of the numerator so that it becomes smaller than the degree of the denominator. Now, this is precisely the same rational expression as appeared in the previous video in this series. And so if you would like to know how to apply polynomial long division, you can go and review the previous video in this series. I'm just going to go ahead and say that the result of that from the previous video was x minus 5 plus 19x plus 29 over x squared plus 5x plus 6. Now, this integrand has been broken down into a linear part, which is very easy to integrate, and this rational part. And now the rational part has a degree which is smaller in the numerator than it is in the denominator. So step 2, let's apply partial fraction decomposition so that I can break this complicated rational expression down into a sum of even simpler rational expressions by partial fraction decomposition. So I'm going to take 19x plus 29, and I'm going to factor the denominator, x plus 2, x plus 3. I'm going to set up the appropriate template, linear function, so constant numerator, linear function, so a constant numerator. Let's clear the fractions and let's see what happens. 19x plus 29 equals a times x plus 3, b times x plus 2. Now, since these factors have values of x which will make them 0, I can, for example, set x equal to negative 3 to eliminate this first term. And if I do that, I will get negative 3 times 19, which I think is negative 57, plus 29. The a term vanishes, and I'm left with b, negative 3 plus 2. Okay, so let's see, we have 57, take away 29, that becomes 22. Negative 22 is equal to b times negative 1, and therefore 22 is equal to b. 28, I don't know what I was thinking. Folks. Okay, 28. So, let us then apply the other value of x to find the other variable a. Let us set x equal to negative 2 and plug that in. If I set x equal to negative 2, we'll have 19 times negative 2 plus 29 is equal to a times negative 2 plus 3. And again, the b term vanishes since it is in contact with negative 2 plus 2, 0. So I get negative 38 plus 29 is equal to a times 1. And in this case, we have negative 38 plus 29 is equal to negative 9. So negative 9 is equal to a. Let's take stock. We now know that a is equal to negative 9. And we now know that b is is equal to 28. 28. So let us take stock fully of our integrand at this point. Our integrand consisted of this linear portion, x minus 5, plus the reduced rational portion, which we now know is equal to this sum. So what are we integrating? We are integrating x minus 5 minus 9 over x plus 2 plus 28 over x plus 3 with respect to x. And finally, we have broken this function down to the point where it is a sum/difference of sufficiently simple expressions. Integrand of x, x squared over 2. Integrand of 5, 5x. Integrand of 9 over x plus 2, 9 natural log, absolute value, x plus 2. Integral of 28 over x plus 3, 28 natural log, absolute value of x plus 3. And of course, the cherry on top, don't forget your arbitrary coefficient.